Good morning, good afternoon, whatever. Good morning, okay. So today I'll be presenting on journey to the secure world of OPTEE from the non-secure world of Linux. I'm not sure how many of you know about OPTEE. How many of you know? Okay, how many don't know? Okay, no worries. But so the talk isn't primarily focused. Okay, let's just start first of all. So we are from Texas Instrument. We believe in upstream first policies. You can see many projects that we contribute to here, and there are much more than that too. So this is who we are. Introduction to the speakers. So this is me, Manorit. I work in primarily Jacinto business unit, which focuses on automotive and much more. And I focus on the security aspects in the Linux side, runtime security. My co-author is Kirti. He focuses on Linux thermal power. Unfortunately he couldn't make it here today. So yeah. So the overview is we'll start with the basics of TrustZone today, and then we'll dive into OPTEE as to what it is, just an intro up to some extent, and then we'll go through the flow of how from Linux to OPTEE everything goes with an example of extended OTP use case that we have made at TI. A disclaimer. So, okay, I'll read it up, guys. So, technology presentation, not a product road readiness or roadmap commitment. Opinions are mine, not of TI's. Okay.
Next slide, make it stand as it.
Sorry?
Make it a bit
Further? Okay. Audible, right?
That's perfect.
So, we'll start with why we need a secure world. So we see that there are many devices that today rely on, biometrics, payments. There are many sensitive applications that we have to run in today's world. And we want to protect all the sensitive data. We don't want that, the keys or the credentials that you are putting in any of the these critical applications should rely in a space that, in case if it gets compromised, can be hacked. So you want to separate all these worlds out in a way that can make it easier for you in case secure for you in case it gets compromised. So and these technologies, the secure world and everything is used in many of the devices today, like phones, IoT devices, payment systems, etc. So the one of the basically the secure world we have is through ARM TrustZone. Like we have it in x86 world too with different terminologies, but today we'll be talking about ARM. And so basically, like you see, we have a non-secure side and we have a secure side. This is how the hardware is in a way theoretically partitioned. What we see here is TrustZone is a hardware-based security technology developed by ARM. It isolates the sensitive code and data. It separates the memory and peripherals and interrupts from the non-secure world. And the switch for all these things are handled in a very efficient manner. It's essentially just a single bit that internally keeps track. That's called the NX bit. So that, whenever the world switch is happening, the page tables, the memory management unit doesn't have to do a full flush to load the context from the secure world. Everything is maintained in one data structure, but the bit tells you what world you are in, and that helps you become efficient during the world switch. And so all these are mostly managed in the hardware, that, what peripheral interrupts should go to the secure world, what memories are being tapped only for the secure world, etc. And we see that, so all these are segregated in different privilege levels, is what we call. So as soon as we keep going downwards, the privilege level increases. And the separation stack is made in such a way that, you can run different codes and different softwares across each of these levels and each of these worlds. So for example, like the things that you might be aware of, EL0 is basically the things that you see in user space. Whatever command prompts you are running, like when you are in a Linux shell, whatever applications you are running, that's the user space that we talk about. That's mostly run on the EL0 of the non-secure side. Then we have EL1. That's the Linux kernel or maybe other OS kernel. So basically, it's the main operating system that's handling the scheduling, etc., memory management, and more things. Then after the OS layer comes the hypervisor. If you want to run multiple operating systems there, so the hypervisor comes one level below the operating system that would handle how to schedule different operating systems in a way and maybe isolate them. Then one level below, if we go down, we end up in the firmware layer. That's the ARM trusted firmware, if you guys know, TFA, ATF. So that's the EL3 level. And as soon as we go to the EL3 level, we have switched into the secure world. So in a way, like I'll cover that too. But basically what happens is you directly can't go to a secure world without reaching EL3. You always have to go down, 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 reach EL3, up, up, up. So once we reach the EL3, there's a trusted partition manager that's available only after v8.4. v8.4, that's the secure hypervisor now. So we see the non-secure world had few things that, you're running the OS, you're running the hypervisor, you're running the secure monitor. Secure monitor is not there, but yeah. So on the trusted partition manager, it's similar. That's called the secure hypervisor. Then we have a trusted OS. That's where OPTEE comes in. So there are other secure operating systems also available, like TrustZone and more. But we'll be covering OPTEE today. And on top of that, now you again have a similar concept of user space on the OPTEE side. So on the secure world side. So what is OPTEE? OPTEE is essentially a secure operating system. It's a trust execution environment designed as a companion to a non-secure Linux kernel running on Cortex-A cores. So it utilizes the ARM TrustZone technology as the underlying isolation mechanism. It has a very modular code base, and it doesn't try to reinvent the wheel. It utilizes the resources and drivers from the non-secure world wherever it can. But it doesn't compromise security on that aspect too. So it's basically like no duplication of code, but having the best of both worlds. And and this concept is that, like I mentioned, utilizing the resources from non-secure world is used heavily in one of the features of OPTEE, that's secure storage. So now, so ARM TrustZone, and what happens is, so now the secure operating system has to communicate to the non-secure world. It needs an interface. So we have interfaces at each level that I showed in the TrustZone. So it uses a Linux TE driver as well to go through the flow flush and communicate. Now, how do you communicate? Like, you are in the non-secure world. Now you need to communicate to something that's running on the secure world. So you have services defined. That's the trusted services that I had shown in the last slide. So that basically are UUID identified. Like you have some UUIDs, and based on different UUIDs, you can tell which service you want to communicate to. And the non-secure world will have that information, and through that you can communicate to the things that are available in the secure world. So now there is no interactive user space as such. That's why we are going through all these UUIDs and services. So there are two types of services, or as we call it, trusted applications in this. So since we don't have any interactive user space, we have a pseudo TA that I'll cover in the later slides, and we have a user mode TA. And the other things about OPTEE is basically like I just mentioned as an overall as to what we are doing with, how we are communicating with OPTEE. But what does it help in? Essentially, it's the secure operating system. You can keep secure storage, like we mentioned. So all the encryption, all the key handling is all done in the secure world. But when you have to write the binary, you can just utilize the drivers from the non-secure world, because everything is encrypted. It doesn't matter, now anymore. And the other thing is you can utilize the hardware unique keys as well that is available. So basically if your SoC has a unique key for each SoC. So what you can do is OPTEE has a mechanism that you can program that key, and then all the encryption, the secure storage encryptions will be using that key. And other than that, you can have a TRNG, true random number generator, hardware random number generator. So OPTEE has services to utilize all that through OPTEE. So the non-secure world, if it ever needs to get a random number, it can go through OPTEE, get the random number, and everything is like in a way partitioned, whatever secure resources you need. So in the last slide, I had mentioned pseudo trusted application. So what is it? It runs in the privilege level equivalent to kernel. So you can consider it maybe similar to a module, not exactly a kernel module, but like similar on those lines. That it's running at the same trust level as OPTEE OS. So it's the part of OPTEE itself. So the size of OPTEE increases if you create a PTA, pseudo trusted application. But the benefit is it has faster loading times. It is existing in the memory at the point when OPTEE is loaded. But another caveat is the bugs can end up crashing OPTEE, or if anything goes wrong, basically you are at the kernel, so it affects you. There are like examples like SCMI, hardware RNG. These are some of the pseudo-trusted applications that exist today, and more as well. That is visible in the link that I've shown. So now what is user mode trusted application, as you would have guessed. Now this is not running at the similar level to what pseudo trusted application was running at. This is similar to a user space on Linux, but the TAs are all signed and verified. So whenever any TA is loaded, it's not that it's insecure. Whenever you have to load something on the user space of OPTEE side, the secure world side, it's all signed and verified. Now we have different types of user mode trusted applications. So one of them is an early TA. So what happens is, as I mentioned, the PTA always exists, in the memory because it's part of the kernel module or similar to that. So early TA is basically what you can do that you want something to be loaded faster, but you want it to be loaded before the runtime of Linux. So early TA is basically a user space, user mode TA that's linked to the OPTEE binary itself. And what happens is the OPTEE has different components. I'll cover that later. But basically, as soon as OPTEE is loaded, the early TA will also be loaded. So it's basically similar to maybe an init service that runs in the beginning, that user space application is loaded as soon as OPTEE kernel is loaded. But the penalty of ELF parsing code still exists, so it's still a bit slower than pseudo-trusted application, but good enough. Then we have REFSTA. So whatever the non-secure side we call, they call it a rich execution environment. So that's the RE. So REFSTA is basically that it is existing on the Linux file system itself. Whenever you need to use any secure service, UUID identified, OPTEE goes, checks that Linux file structure, and there's a designated space where you have to keep these. It will go find that UUID, load it. So it's basically going through Linux REFSTA, that's what we call it. And so now the binary has to be loaded in the secure world. So the binary copying from the non-secure to secure world happens. So there's a bit more latency for the loading time in this. And then there is a secure storage TA. Basically now, sometimes you want to encrypt your trusted applications. Whatever you're making, you don't want it to be leaked or whatever. So now it uses the underlying secure storage mechanism. So whatever hardware unique keys you are using, so it can be protected per device too, whatever the secure storage TS you have. So overall, if you want to summarize how to do this trusted application, if you are using hardware drivers, you should essentially be similar to a pseudo-trusted application that you want to, be at the kernel level. So go for a PTA that time. If you need it up early before Linux is up, NT supplicant is up, but you don't are necessarily interacting with the hardware, So you can go for a user space application at the secure side. So, but you need it to be up early, so go for an early TA. Now, does the TA need to be protected confidentially, like the encryption? You don't want it getting out. Go for a secure storage TA. If you are fine with none of these aspects, maybe go for a REFS TA. Like, you don't need fast loading. Of course, the loading times and all would also matter in this flowchart. This is a very simplified one, which I could think of. But yeah, maybe this would help you, choose as to which one you should be going for when you are designing trusted applications. So now the control flow of OPTEE. So there are three core components of OPTEE. You have an OPTEE operating system. You have an OPTEE client. So OPTEE operating system is basically the core operating system that is running on the SEL1 stage, the secure side EL1. You have an OPTEE client. That is the user space daemon. Like on the Linux side, you have, like from the Linux user space also, you can go down and then reach the secure side. So you need something communicating from the user space too. So OPTEE client gives you a TE supplicant daemon that is basically running, and that helps you with the, and it gives you the TE client libraries too. These all are linked to any of the user space application on the non-secure side that can help you communicate the full flow from non-secure side to the secure side. And then you have the OPTEE kernel driver, which I had mentioned previously, is the underlying layer on the non-secure side, EL1. So we'll just go through the control flow of OPTEE step by step from a perspective of a trusted application. So in the beginning, whenever you're writing a trusted application, you have to initialize the context. So what it does is you have a host application that is the EL0 on the non-secure side. So it initializes the context. So it goes to OPTEE client. That's the T client libraries that are linked. And in the bookkeeping, what the T client library does is it opens the /dev/TE device. So whenever you have OPTEE running, it opens that device and it stores it in a context. So it's just a basic call. That's it. Now, once you have the context initialized, you go and start opening the session to the trusted application. So host application calls TEC open session. What happens is now you go to OPTEE client. OPTEE client creates a shared memory where it can use for communication, and it passes that shared memory to kernel through arguments through an ioctl call. So now from the user space, since an ioctl call happened, we are now in the EL1. We are in the kernel. Now in the kernel, you see, this is the TEC ioctl function. So you have different handlers here. And one of them is TEC open session, which we are currently looking at. So what it does is, this is the TE generic framework that we have. It goes to, so you can have different types of TE too. So it goes to the OPTEE or AMD TE or etc., whatever TE you can make. So through the framework, we reach the OPTEE TE driver. So from there, OPTEE TE driver takes the user space, passed arguments, structures, etc. It figures out the client UUID who called it for bookkeeping, and it creates an own message like OPTEE message command open session that, this is the call that user space is asking for. And then it passes all these buffers that it had allocated, the user space had forms it, and then it goes to the next level call, that's the SMC call. So from, I'll be skipping the hypervisor because for simplicity purposes. So now we are directly reaching the firmware from the Linux side. So now we have reached the EL3, that is the secure world context, the first secure world that we end up in. So now that is the trusted firmware ARM that we are running in today. So in trusted firmware ARM, you see there's a OPTEE SMC handler. So as soon as you end up in the SMC call, this is the handler that would handle the world switch. It stores the context from the non-secure world. It switches the context to the secure world. So now that function essentially handles two things. So whenever you end up from a non-secure world, it handles that too. If you end up from a secure world, it handles that too. So currently we are looking at the non-secure world caller when Linux is calling to TFA. So there's another functionality that you don't need to load OPTEE at the boot time itself. If you want to load it at some other time, I think you can use the OPTEE image loading functionality with OPTEE allow SMC load. I haven't dug deep in this, but I found it, so I thought it's worth a mention. But what would happen in our normal cases, we would go to the regular SMC handling. So it saves the non-secure CPU context, checks if OPTEE is loaded, initialize the secure CPU context, sets up the entry point based on the SMC type. You can have a fast SMC type or a yielding SMC type. And then after that, it transfers the control to OPTEE. After passing all the parameters that it received from the non-secure world. So now we see all the parameters are getting passed. We have reached the EL3, and from there, we'll move forward. So now, this is the other side of it that I'm covering here itself. That's basically when, from the non-secure side, we just covered the aspect when non-secure side, the Linux was reaching EL3, but I'll cover what happens when the secure caller also reaches the EL3. That's the same function, OPTEE SMC handler, that handles this. So when the secure world caller, OPTEE returns to TFA, it can, do different things. So as I mentioned, it can handle power state control as well. So whenever OPTEE, suppose a CPU bring up happens and that call is supposed to reach to OPTEE. So OPTEE would reply with certain codes. So these are all mentioned here. But for our current use case, what would happen is we would go to the option C, that's the normal operation returns, that OPTEE completed a request and, of the open session, and then we are just going back. That is what would happen. So now from EL3, we have reached the SEL1, that's the OPTEE. This is the first call that we have ended up in OPTEE. So now, as I mentioned, it would either be a yielding SMC call or a fast SMC call. So yielding SMC is basically a functionality that, OPTEE will spawn threads in its own environment so that, if any interrupt comes, you don't have to, end up worrying about latency, numbers, etc. It's still up to some extent real-time performance because the thread can be preempted and the call can go to non-secure world and then come back to the secure world when that interrupt handling is finished. Fast SMC call is not preemptable. It doesn't create any threads. It doesn't enable the interrupts. So it should be fast by definition. So this is one of the fast SMC calls that I mentioned. And these are the standard SMC calls that we have which enable the interrupts. And open session is one of them under the yielding SMC call. So now from there, we traverse, and we reach the init session. So once we reach the init session, now there's the differentiation between if it's a pseudo-trusted application or a user mode trusted application. So if it is a pseudo-trusted application, it is already up in the system. So basically, the UUID and everything is passed through all the chain. And then so the trusted application on that pseudo-trusted application side would have an open session entry point. So now you would just jump to that. The story of pseudo-trusted application reaching is over. For the user mode trusted application, we are still not there yet. So now we diverge and now we will go to a user TA enter session. And from there, you would now switch the context to the SEL0. That's the user mode side of the secure world. So now you would switch the context. You would go to the entry point of the user mode trusted application, whatever you had. Now from there, you would find, UT entry. And there you would again see that, now we are in the user mode open session. And from there, it will now jump to a UUID identified service, what we had for the user mode trusted application. And then you have finally reached the user mode TA2. So this is how the initialization and the open session happens. So now you have a communication path with OPTEE established. What can you do with it? So now OPTEE has different invoke command mechanism. Now this would be trusted application based itself. You can define any commands that you want. So for our extended OTP application, we had like read MMR, write row, lock row, these commands that were specific to our use case. So this is what the invoke command we registered, and we registered the sudo trusted application. What is an extended ODB application? So basically, these are like extended efuses that we have on our K3 SOCs. And these can be programmed for any of the use case, but since it's an efuse, we don't want it to be directly accessible by the non-secure world. So we had a mechanism that you can make a pseudo trusted application out of it and give the efuse access only to the secure world. Why OPTEE? As I already mentioned, these bits are exposed, and our TI foundational security, that's the software that's running on a Cortex M4. That's a system controller. So these are exposed to the secure world, and whenever we have ARM TrustZone, it exposes all these sideband signals so that the other cores can get to know if it's coming from a secure world or a non-secure world. So at a system integration level also, the TrustZone gives you that information if you are running from a secure or a non-secure context. You can use that information to pull this or do whatever you want with it. So from a perspective of the trusted application, you can define now parameters that will be passed to invoke command. So if you are running a command like, what do I mention? Okay, this is the write row. So basically when you are writing the row, you need to tell what do you want to write, the data, the mask, what bits you want to write, what index you are wanting to write at. So all these you can configure as parameters in that trusted application. These will be passed from the user space of the non-secure side to the secure side again. And then, OPTEE would have all these information. And then this is the trusted application side that we have, the pseudo trusted application. So you see that we are once we get that information, we are calling our TIFS, the system controller, and then we are passing all these parameters. We are not doing any, like this is just an example, but this can be made specific use cases, like you can have different trusted applications that are handling different set of efuse bits, and they have different purposes, like something could be for OT updates, some software updates, something could be for something else, some key management. You can utilize all these in form of different trusted applications that are just handling different set of efuse bits. All this differentiation you can do at a trusted application level instead of keeping it at a system controller level. So this is how we are now from the user space. You end up doing the call as a user space application, that OPTEE example OTP key writing. You write with the value, the mask, the index. It all goes through the flow that I had mentioned in the past. And at the end, we end up writing the OTP bit in the efuse. Next, we can just read it up, and then we see we have dead beef. You are clicking a photo, I saw. Okay, these are the references that I saw, and I would like to thank Texas Instruments, the Linux Foundation, for giving me a platform. And yes, thank you so much. Any question? Yeah.
So in your extended ODB app, so you have a user app in the non-secure ES0, right? Running?
Yes, so this is a pseudo trusted application, and so now we don't have a so you just have a host binary that's using the UUID that's in the PTA, and from there it just connects to that. So yeah.
And you're doing what reads and writes through
The Linux user space application, correct?
Yeah, and so I was wondering, is there a reason you didn't use the kernel's T-cell system to expose a device and let you essentially do those reads and writes?
So as I mentioned, we didn't want to give this access. So we didn't want to give this access to the non-secure world by default. So like I mentioned, the TIFS, the system controller that we have, like checks that if the request is coming from a trusted entity, and the ARM gives the sideband signals to check if it's coming from a secure world. So you can use this in a system architecture fully using the TrustZone. And you don't want, the Linux to be directly writing to like efuses. Like we have our TI-SCI that's handling it.
Sure, but what I mean is the kernel can expose through the TA and through OPTEE using a normal device.
Which one? Sorry.
It's the T subsystem.
So you're telling the T subsystem can?
It can essentially do a bit of the UUID handling and the communication to be trusted out for you.
Yeah, it does that. So we just have made a pseudo trusted application. We didn't go. I just explained all that. That's it. I am not getting your question or what?
I think that maybe we can talk about it afterwards.
Okay, sure. I'll check it. Yeah. Yeah.
That's a question regarding testing. So especially the efuse part is a bit problematic because once you burn it, there's no way back. So is there any dry mode or something like that which behaves like with burning the fuse but which doesn't actually burn?
So the testing that I went about it is so first of all, without writing to the eFuse itself, I just did the flow flush that all the communications to the OPTEE were reaching correctly, and what I wanted is actually going there. So that is the first level of checking that I did. After that, when I started writing, I had a few hiccups in the beginning that, the bits were flipped and all. All those I had to figure out. But yeah, I did burn some fuses. But after that, I think, I understand it's a complicated procedure. And that's why we don't have, what do you say? So this is just a example application that we have so that it can provide you the infrastructure, and whatever testing we could do, we have done at that point for this. Yeah.
Some of the SSCs have shadow registers for fuses.
I did not understand.
Some SSCs have shadow registers for OPTEE, and you can just sort of dry write into the shadow register and link back and work with that for some testing.
Oh, okay. I am not aware of that. Okay. Yeah.
I have also a question on test. Is the system or tooling that we use for debugging and profiling on Linux interface, is it also available on OPTEE?
So I used, I think, Prince only. There weren't much things. I was using JTAG based debugging for mostly the purposes to know where I'm ending up in. And I think that was mainly the things that were helping me, JTAG and Prince. Yeah.
JTAG with louder buff or something else?
Sorry?
Do you use only louder buff or something else?
I think we were using the XDS itself. Yeah, so we have a XDS 110 on our EVMs, so we were using that for the debugging purposes. With OpenOCD. Yeah. Hi.
In the previous slide, you showed like a trace of,
This, okay.
How does this come about? Are you?
Yes, so we are the ones logging, and this is like the full flow trace level. So our TISCR driver has some flow prints that we have enabled, and this was with full debug logs so that we could see trace as to where we are ending up in. So you can see that, we are verifying the thread. All that is like the TIFS, the system controller communication that is happening, that we are checking all these things.
So this gets written to standard of.
Yes. Not always, like you can configure the debug access, but yes, I don't think there's something like function tracer in Linux or ftrace. Yeah, I am not aware of it if it exists. Yeah, hi.
How about recommendation for how to use secure EL2?
Secure EL2, oh, I didn't. Okay.
Set Linux hypervisor just one by one or another technique?
Oh, for loading the SEL2.
One secure EL2 OPTEE binds to the one no secure Linux one.
Sorry. I'm not aware how to load SEL2. Yeah. Okay, I think we are at time. Okay. Thank you.